Welcome to today's lecture. We shall continue discussing on the inclusions, fluid inclusions, the change in their morphological characteristics and compositional characteristics when they are subjected to stress or deviatoric stress condition. And we just in the last class we discussed the results of experiments which are done on hydrostatic stress, where no much of difference or no much of change is brought about to the inclusion other than just the shape becoming more tending to become more regular. And then let us have a look as to what happens in the conditions where the variable degree of deviatoric stress is applied on the sample where the inclusions were inclusions were known to be there and their characteristics is also known. The diagram on the right hand side, which is also taken from the same experiments which were discussed before. So, here this particular small region as to shown here are the entrapment conditions of the inclusions that are present in the sample corresponding to their original conditions of formation in the area, in the locality from where they were taken, in a particular corresponding to a particular situation, as I have said that they are taken from a gold deposit which was studied before. And then these conditions represent the steps by which the pressure temperature conditions are increased, and these corresponds to the hydrothermal stress hydrostatic stress regimes, where the temperature pressure conditions greater than what corresponding to their original conditions were applied. And these are the isocores of the range of isocores from the microthermometric experiments that was done on those natural inclusions, and this fan shown by the dotted line is basically the region in which these isocores could pass. And this condition corresponding to the situation where the temperature about 700 degrees Celsius and higher and higher the pressure that was given. So, here the deformation experiments conditions were shown here, and without getting into the very detailed the discussion on the experimental results, which I refer you to the original papers, just to have some idea that in a situation where the inclusions are subject to deviatoric stress, in a smaller extent of the deviatoric stress experiment, what basically results in a change in the shape of the inclusion. If this represents the original intact inclusion, then we could have an inclusion where the shape could possibly be distorted, whereas the volume and in terms of the proportional or compositional characteristic of the inclusion will remain same, and that is why it could be denoted as an intact inclusion. Now, situation where the deviatoric stress condition is applied with a higher del rho, there the situation what happens is that if this represents the original inclusion which was there in the sample before the experiment, then the result of the experiment shows that this inclusion is dismembered into something which you can call as a relict inclusion, which is in shape which is distorted, and also the volume property is also changed from here and is surrounded by this small cluster of inclusions which were basically designated by these authors as neonates. And characteristically the arrangement this relict inclusion and this neonate or the newly generated or newly created inclusions, they do follow roughly the plane. They are arranged on a planar or discoidal kind of arrangement, and they are parallel to the minimum principal stress axis, that is sigma 3, when the stress sigma 1 is actually vertical, which is applied through the piston apparatus which is used by these workers here. And then it is so qualitatively speaking, the inclusions then, or the original inclusion has been dismembered. So, definitely there is change in the volumetric property. So, we cannot expect that these relict inclusion and the neonat also are present in the compositionally also similar to the relict, but some change in the composition which we will discuss a little later. So, compositionally we would also expect that they would have undergone some change. Now, in addition to the change in volume, which will always make them the density to have been different and would follow a different isochore, it is also quite likely that what we discussed before, that these neonats from these inclusions, or the newly created inclusions, will also have the same situation as differential loss of water from them. They would also be, because these experiments were conducted on aqueous carbonic inclusions. So, this fluid as dismembered aqueous carbonic inclusions also would are most likely to have undergone the preferential loss of water and are more likely to have undergone some compositional differences. Other than the fact that they were the condition corresponding to the creation of these neonats, or the newly created inclusions, is also higher than the pressure temperature condition in which they were formed. So, they are the isochores of these neonats are also going to significantly deviate from the original inclusions. So, in the lowest strain, where delta sigma is about 92 Pascal. So, most inclusions survived with changes in shape to irregular or flatter. They become flatter in the shape, and this plane on which they are flattened is actually subparallel to the sigma 3, that is the minimum principal stress axis. A few dismembered to relict and neonats with the same planar arrangement. When the delta sigma is increased to about 135 megapascal. So, most inclusions become irregular or flatter, and the newly created inclusions, the neonats, arranged in planes parallel to sigma 3, and the quartz plastically deformed, shown by the undulatory extinction on such planes, which is actually is a result of the fact that the water which is preferentially lost from this newly created or the neonats, they do escape, and then they facilitate the plastic deformation within the host quartz grain, which is very clearly they come out to be different from the rest of the quartz grain in terms of showing undulatory extinction on such kind of planes. So, when it is medium strain to about 162 megapascal, all the features which are described in step 2 are more or less the same with greater intensity, and when it is again increased to 222 megapascal, there are strong changes in the inclusion shapes, large relict inclusions surrounded by fans of necked fluid filled branches with isolated neonats, and when it is the highest strain, then the greatest extent of plastic deformation in quartz with. So, what happens is there is mismatch of the C axis on different planes, and the newly created inclusions, the neonats, lie on planes parallel to sigma 3. So, that is the situation which happens. So, the observation is that when the with increasing delta sigma, it always give rise to greater degree of plastic deformation in the host quartz grain. Just to have been taken from the photographs have been taken from the same source as shown here, just for because it is not possible to make a very detailed description in this particular, and the whole objective is to just discuss some of the important aspects which would always be carried in mind while looking at the inclusions in natural samples when we do this as a routine work on the fluid inclusions in different types of terrains, different types of samples, and with the fact that these kind of textural changes in the inclusions is also has a strong dependent on the size of the inclusion. That is what for the inclusions which which were discussed here, in most of the cases we see that the deformation or the change in the shape is more in case of larger inclusion than in the smaller inclusions. So, this is one situation where in the deformation experiment, it is good seen here, if this is the, and in this kind of experiments there is always a limitation, because to get back the exact same inclusion on which the earlier data were taken, or the inclusions which are earlier studied, and again after the cylindrical cores were cut from such sample and they were subjected to the experimental conditions, and then again studying them under the microscope definitely involves a little bit of uncertainty, but those uncertainties notwithstanding, the results of such experimental work definitely give us very important useful insights to the study of fluid inclusions in general. So, what we could see here, that this is an intact inclusion, and it definitely the inclusions in its surrounding, it clearly shows that the same inclusion is the one which is after the deformation experiment, and it is clearly has become flatter and the surrounded by the and is by this kind of features, which shows the result gives a very good idea as to what exactly happens, and this is in a higher extent of the deviatoric stress, where this inclusion is very much thoroughly changed in its shape and in its and having the neonates arranged on a plane, on a discoidal plane which is parallel to sigma 3. Such kind of experiments, the results while extrapolating to natural conditions, there are certain points which should be kept in mind that the kind of deviatoric stress that is applied in these kind of experiments is built up in a much faster in the experiments than what generally happens in nature, where the process operates much slower, and such slow build up of deviatoric stress is possibly cannot be done in an experiment, and that would definitely give rise to some difference in what we observe in the experimental run products and in natural inclusions. And the nature this the magnitude of the deviatoric stress also is high in the experiments compared to what happens in nature. The rate at which the strain is applied is almost 4 to 5 orders of magnitude higher than the experiments, higher in the experiments than what happens in nature. And then the quenching after experiments is also quite faster than what happens in nature, because if a particular set of inclusions which were trapped in a host mineral pertaining to certain conditions of pressure temperature, and it is being subjected to deviatoric stress, and the recovery or the rate at which the sample is actually quenched in nature is much slower than also what is possible in the experiment. So, that this faster quenching also does give rise to some other kind of features on the samples, such as some later horizontal cracks. Of course, they can be distinct, they could be distinguished because there will not be any fluid inclusions entrapped in such kind of cracks which develop as in the process of rapid quenching. So, these limitations notwithstanding, results of such experiments match significantly to natural deformed samples. It is also believed that inclusion bearing samples facilitate deformation, and the planar fabrics also develop due to the planar arrangement of the secondary inclusions produced during such deformation. It is actually in many such natural sample examples are there, that if such kind of preferential loss of water is actually what is happening in nature, then or whether any aqueous fluid that actually is coming to play at any particular time during the process of deformation and recovery from deformation, they facilitate the plastic deformation, and sometimes the very closely spaced inclusion field micro cracks, they do give a fabric to the samples, which generally is not a feature which is primary to the samples in which we are studying. Just a little bit of scenario which is different from what has been just described here. So, compositional, so you could see here that the this as we discussed, that these neonats are the newly created inclusions will have volumetric properties which will be different or will be shifted from the inclusions which are originally studied. So, in case of the aqueous carbonic inclusions, the intact and the relict inclusion mostly retain the original composition. This deeper shaded region, which is actually the isochores fans of the newly created inclusions of the neonats, and the lighter grey shade actually the isochores of the precursor inclusions. And as we have as discussed, these experiments, they result in intact and relict inclusions, they mostly retain the original composition. The newly created inclusions, the neonats, have higher concentration of carbon dioxide and salt because of the preferential leakage of water, and this kind of higher or the increase in carbon dioxide is also higher where the del P is greater. So, with as del P is increased, the inclusions proportion become more and more richer in carbon dioxide, and that is the reason why these newly created inclusions have very high fugacity of water, and this is also is one of the reasons why the water would tend to escape through the from these newly created inclusions through the defects or the dislocation planes in the host crystal, and that facilitates the plastic deformation in the host quartz and is observed as greater extent of undulose extinction on those kind of planes on which the newly created inclusions are arranged along with the relict inclusion. So, as compared to the just described situation in which the experiments were done on natural aqueous carbonic inclusion, this similar type of experiments were also conducted by the same authors on pure aqueous inclusions or H2NaCl inclusions. And what insight we can get, the situation is more or less the same. They do also develop the newly created inclusions which are arranged on planes which are subparallel to the minimum principal stress axis sigma 3. In addition to that, actually here it sometimes when we study natural inclusions in deformed terrains, and if there has been a fluid, sometimes it is difficult for us to know exactly the stress condition because the pore fluid pressure could not be ascertained, which we will be discussing in one of the case studies. So, if you look at this diagram, then it will be of some use, like it has been shown here that the experiments were basically the results to be looked here is within the stability of the alpha quartz, and these are the isochores of the original the pristine inclusions, and these are the isochores of the large flat subhedral neonats. So, here since the temperature is known is 700 degrees or in this case this whatever, because we know the temperature of experimentation, and these are the isochores of the neonats. So, we can always get the pressure corresponding to the neonat, and that could give us some idea as to what is the value of the maximum principal stress in such kind of situations. So, these could be results of such kind of experiment, and the isochores constructed on the newly created inclusions as seen from here, they give us the idea about the value or the magnitude of the of sigma 1. That is this corresponds to the sigma 1, and this circle corresponds to this corresponds to the field square corresponds to sigma 1, and the open square corresponds to sigma 3. So, we can get the values in natural conditions such kind of stress state of stress in the particular rock in which we are studying them. So, with this, and it has to be kept in mind that the accuracy or the dependability will always be a function of the accuracy by which we are able to calculate the inclusion density and the isochore. This is more applicable to the aqueous carbonic fluid, where for example, in this case when the aqueous carbonic isocores were drawn up to pressure of almost 7-8 kilobars, there we also do have to consider what formulation we are using and how much of error it involves, and we always tend to get more refined or to PVTX relationships in such kind of fluid mixtures, so that their applicability to natural conditions will be much more definitive and better. So, with this little bit of discussion on the application of fluid inclusion studies to natural samples, where there are indications that the samples or the terrain has been subjected to later deformation, and indicating that the inclusions which were trapped in the original conditions were subjected to evolution on non-isochoric paths. We gain some important insights from such kind of experimental work, and hope that such experimental work will be done on situations more closely or more corresponding to diverse compositional characteristics of the inclusions, and taking into consideration or refining or improving upon most of the difficulties in such kind of experiments and the uncertainties in the interpretation of the results. Now, we will will discuss something on the same situation as the application of fluid inclusion to study of deformation of rocks, and in this we would just like to discuss this concept of what is known as the concept of fluid inclusion planes. Through this cartoon I have just tried to explain what would exactly it be. First of all, we intend to apply fluid inclusions to understand deformation of rocks, or broadly to structural geology, and here the most fundamental aspect of this kind of exercise or this kind of work is that we do collect the samples from the field with proper referencing of the of our identification of the different types of planar features on the rock, the fabrics, and which we ascribe it to the different stages of deformation corresponding to the, and then when we reconstruct in terms of the stress ellipsoid in terms of the maximum and the minimum principal, maximum intermediate and the minimum principal stress axis, and collect what we call as the oriented sections, oriented samples from the field with the proper marking of the azimuth, the orientation with respect to whatever planar features that we have identified in the field and have ascribed to what kind of deformation stage in the rock, which phase of the deformation and which exact plane that we are looking at, what actually it represents. So, once we I would definitely suggest to consult some experts as well as what is available in the in terms of the method that is to be adopted for collection of such kind of oriented samples in the field. And not only that, once the oriented sample has been collected from the field, the sectioning also has to be done in such a way that the surface of the section, if the top is representing the surface of the section, the surface of the section is also very well referenced with respect to whatever planar elements that we are interested in. With the fact that in a natural sample, the what we are looking at, so essentially would be the inclusions which will be arranged on planar arrays corresponding to the brittle fracture or the mode 1 fractures fracture field, and these are the fractures which are filled with the fluid and later on they are sealed with the host mineral as secondary inclusions, the inclusion plane. So, there may be multiple sets of such secondary inclusion the fracture planes, fluid filled fracture planes. So, now here just looking at this particular example, what has been shown here is that let us see that there is a plane. This is the this is the plane on which the inclusions are arranged. And now, so when we are seeing them under the microscope, it is possible to not only just to identify or to ascertain the arrangement of this particular array of inclusions which is arranged in this particular plane, and let us say that there is one plane of this constitute one fluid inclusion plane. So, this fluid inclusion plane in terms of the attitude, that what is the depth of it and the direction, can be very well ascertained if we have a graduated microscope adjustment knob with a scale, and which could be very well calibrated, and the measurement can be done taking into account the least count or the kind of error which is involved in it. And as shown here, when we are seeing them under the microscope at a particular position of the microscope stage, we will see the inclusion plane, the array, as like this on the two dimensional field of view of the microscope. If we raise or lower the microscope stage, this particular array of this particular linear array of inclusion would tend to move in a direction, for example, which is shown here. If we are raising the stage of the microscope, then we are focusing the plane at deeper and deeper parts, and so this array would look to move to the right. Now, we know the amount of the movement in the horizontal direction, and also if we have calibrated our microscope adjustment knob in a way that exactly what is the vertical movement that has taken place for this particular horizontal movement, then we can easily calculate what is the depth of this particular fluid inclusion plane. So, this looks to be simple, but definitely it needs a lot of good amount of exercise, and to measure the or to ascertain the fluid inclusion plane and know or exactly calculate what is the attitude of this particular plane. And then once we know, then we can always put it in the reference of which the surface fluid inclusion, the surface of the fluid inclusion section is, what plane does it correspond to, and what direction, and so on. So, these fluid inclusion planes are being studied by many workers, many of the experts who intend to apply the fluid inclusion techniques to understand deformation in rocks. So, the situation is exactly what we are getting from this kind of fluid inclusion planes, that the fluid inclusion planes are definitely the mode 1 cracks, that means there is no shearing, and they are on the sigma 1 sigma 2 plane perpendicular to the sigma 3 axis, and give important information on the regional stress conditions. And the fluid inclusion planes are well characterized in minerals that crack as per the regional stress field irrespective of the crystallographic axis, and quartz very much satisfy to this particular condition. And so, when present in multiple intersecting sets, the chronology needs to be well established to interpret in terms of changing conditions of stress. Each set of FIP represent discrete phase of fluid activity and indicate the PT conditions of paleo activity. So, here is the expertise. So, once if this particular work is fluid inclusion work is being done, then most of the part are essentially that the understanding about the mechanism of the formation of the crack and the direction of the have done good amount of the stress analysis in the field, and after on this particular background, when these fluid inclusion planes are measured, and there are multiple sets of fluid inclusion planes, and since they are fluid inclusion planes, they are likely to have entrapped fluid of any particular composition, means they could be aqueous biphase, aqueous polyphase, or sometimes, as we have shown before, there could also be aqueous carboning inclusions which are likely to be entrapped in such kind of fluid inclusion planes. And routine microthermometry can be done on such fluid inclusion planes their salinity, density and their isocores also can be plotted, and they will be the ones which are going to give us the important information about the paleofluid activity in terms of the fluid pressure, which could be determined from the isocores of these inclusions. The fluid pressure, which controls the nature of the failure and the stress analysis, infer from it. The effective vertical stress depends on the fluid pressure, because that is the one which we are mostly interested in to calculate, to know the effective vertical stress, which is essentially a function of the fluid pressure. And the early workers, like the one which is referenced here, they very strongly vouched for such methodology of fluid inclusion studies in relation to structural geology, and they visualized a very bright future for the study of the fluid inclusion planes. And as we will be elaborating from a couple of case studies, we will see that yes, fluid inclusion planes have greatly helped in understanding the ways that the rocks have deformed. It is not only just that, much greater implication in terms of the tectonic evolution of any particular terrain. So, we will continue discussing in the next class. Thank you.